Hi everyone, we are back and now we are going to do our problem, which is bend, don't break. So let's do some bending problems. So first things first, metallic beam, length of this, width of this. So length, that's going to be L, width, base, this is going to be our thickness. I equals BH cubed over 12. We're going to set our coordinate system, X, Y here. We need to write out E times I times where E is going to be our metallic beam, 100 times 10 to the 9, 10 to the 9 Pascal, 100 gigapascal. Y quadruple prime X equals, I'm going to set this as our origin, X equals 0. So I'm going to do it, let me erase that. Let's zoom out a little bit here. You can tell I'm a little bit under the weather, but it's okay. Minus 1.7 times 10 to the 3 newtons Dirac delta, x minus L over 6, minus 4.5 times 10 to the 3 times Dirac delta of x minus 4L over 5. There we go. Oh, excuse me, I'm going to sneeze here. Excuse me. Oh, excuse me. There we go. All right, let's go ahead and get to solving this problem now. So I'm going to basically type all these values in. We're going to quit our kernel. We are going to go to our, we are working with a material that is 100 gigapascals, a length of 76 centimeters, so times 10 to the minus 2, a width B of 44 millimeters, and a thickness of 1.8 centimeters. Oh, excuse me. All right, so we have that. We're going to do minus 1.7 times 10 to the 3 minus x minus over 6, and we're going to copy this. Come on. Uh-oh, Mathematica is giving us a little bit of trouble here. Don't fret, don't worry, it will respond. There we go. So I'm going to copy this, and I'm going to go minus. We're going to do 4.5 x minus 4L divided by 5. So that's going to be our values. So now what are our boundary conditions in this problem? Well, we know that our y of 0 must be equal to 0. Our y, the slope at 0 must be equal to 0. At L here, we have y of basically no restoring moment. L must be equal to 0. Additionally, we know here there needs to be a restoring force here. So I need to set basically some of my forces equals 0 at the origin, actually in the y, equals, I'm going to call this just V minus 1.7 times 10 to the 3 minus 4.5 times 10 to the 3. And I'm going to solve for V. And that's going to be my, basically, my V is going to be equal to E dot I dot Y 1, 2, 3 at 0 as well. So let's go ahead and plug those in. Y of 0, Y prime, Y double prime at L, and I'm going to solve. So V minus 1.7 times 10 to the 3 minus 4.5 times 10 to the 3. So that equals 0. So I'm going to say my triple prime at 0, y times I times this equals 6,200. Those are all my boundary conditions. So we got those. Let's click it. We've got this now. We can now plot it. Oops. Let's plot that. That's our solution. So that's our deflection equation. Let's plot it through here. And that looks pretty good. Wow, I like it. So let's go ahead and find where is our minimum or maximum deflection. I should start it around 0.76, that looks good. Around this many meters, good. Oh. And then my bending moment will be here. I can find my minimum as well for my bending moment. Plug that in. Does this make sense? So minus this, at the top of our beam will be in this position, will be in tension. That is true. There we go. This looks fantastic. So this beam cannot deflect more than 27 centimeters, and the stress cannot exceed the yield stress of the purple curve. So will it deflect more than 27 centimeters? I believe not, because the deflection is 0.22. So it will not deflect more than that. So that is good, but we're about a gigapascal. So if we look at the green curve, or actually, excuse me, purple curve, yield stress on my purple, it's about, I'd say 40 megapascal. So not going to work. Our stress is much larger. All right, we got it. Really, really, really nice. Beautiful. All right. So dynamic mechanical testing is mystery material A versus time. Tested new materials B and C. B is a visco that is less solid than A, and C is a viscous fluid. What symbols correlate to storage and loss modulus? So if we look at this curve, at long times, I should behave. So once I have this crossover point here, which is my T relax or relaxation time, also typically like tau in polymers. So here's my viscous. This is my solid-like response. Short times, I should behave like a solid. So empty is going to be storage. Filled is going to be my loss. So E prime, G prime, E double prime, G double prime, not triple prime. So there we go. Got it. So this will be the value. So we need something that is, less solid. So this is for A. So I'm going to also signify that this notation, these materials are A. So black is A. I'm going to do blue is going to be B. And blue is going to look like it is less solid than A. So here in this curve, we're solid for this much. So our transition point here needs to actually occur sooner. So I'm going to draw like open square, open square, open square, and then let's see. Open square, open square, open square, open square, open square, whatever. And then I'm going to do solid, 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 solid. So actually viscous, 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 excuse me. So we can see here that this is the material A is more solid than our material here. Because again, we're only solid from here to here. This other material is solid from here to here on this axis. So even at longer times, it's still remaining a solid. And then material C, which I'm going to denote as my purple, material C, is going to be a viscous fluid. So I'm going to have loss, 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 loss here, and then open, 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 storage, open, 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 open here. So this would be my relaxation time of this material here. This relaxation time would essentially be basically zero. So there'd be a zero relaxation time here. It wouldn't be infinite because that would be for a metal. So it's an instantaneous response, but I'm not really expecting you to get that necessarily. So we've done this, and then we've explained it. What's the last thing? If we change the x-axis temperature, what would be the values of high and low rate? So if this was temperature, time temperature equivalent, so this would be high, this would be low temp. If it was rate or frequency, this would be low frequency. Again, low frequency, it's going to be elastic or viscous response, excuse me. This would be high frequency here, solid-like response. And that's it. So there you go. Bend, don't break. I want to try one little thing here before we leave. I wonder if we set this to be equal to 0. Yeah, but you can also say there's no restoring force at that moment too, and we're going to get the same answer. Or not, restoring force at the location. Yep, there you go. So it's even easier. All right, that is it. So we'll see you in the next video. Thanks. Bye.